Good afternoon, everybody. Allow me to start the lecture discussion. Okay, last meeting we were able to discuss all about fundamentals of atomic structure, and then we finished up until this slide. So let's have a quick review. Okay, recall class that the correct representation of an atom, given its elemental symbol, is you write the atomic number designated with letter Z on its left side, bottom part, and the atomic mass is written on the left side, topmost part. Okay, so say for example, sodium, recall that it has an atomic number of 11. So that is where you write the atomic number, or also equivalent to the number of protons. And then it has an atomic mass of 23. Okay, so that's how you correctly represent an atom, reflecting its elemental symbol, atomic number, and atomic mass. Now, since we were able to mention about the number of protons, please take note also that for a neutral atom meaning no charge atom, the total number of protons is always equivalent to the total number of electrons. And recall that this atomic number of sodium, again, that is equivalent to the number of proton. Since the given atom of sodium here is neutral, you are not seeing here any charge like negative or positive charge, then we could tell that proton number is equivalent to the number of electrons. So since it has a proton number of 11, then the electron number here is also 11. Okay, let's have another example. For example, for the atom of the element chlorine, chlorine has an atomic number of 17. So meaning to say that is also equivalent to its proton number. So if you are asked for the number of electrons for a neutral, this is a neutral chlorine atom kasi it has no charge carried. So the number of electrons is also 17. So that's how you determine the number of electrons. Equivalent lang sa number of proton if neutral. Okay, so take note of this statement. If neutral atom, number of protons equals number of electrons. Now, if ever you encounter a charged atom, let me write it. If charged atom, or the term we refer to a charged atom, those are also ions. And we have two types of ions, the cations, and then we also have the anions. Okay, so if ever charged atom is given and you are asked to identify the number of electrons, take note the proton number this time is not equivalent to the number of electron because it's already charged. It carries a charge, a positive charge or a negative charge. Okay, let's say for example, the given is sodium ion. And in the list of ions that I have provided to you, the ion form of sodium metal, it's an A+. Okay? And again, it has an atomic number of 11. So this time, if you will be asked for the number of electron, it's not already 11. Okay? Because it's already a charged atom. So how do we identify for the number of electrons here if it's already charged? Okay, so you'd simply refer to the charges. The charges that is being carried by the atom that will help you identify if that particular atom loses or gains electrons. So just take note, if it carries a positive charge, okay, meaning to say that atom loses electrons if it carries positive charge. So for those cations, those atoms that forms cations, they loses electrons during chemical reaction. And then for the negative ions, if it carries a negative charge, what happens during chemical reaction? They gain electron. Okay, so do not confuse the negative sign as subtracting or minus. Okay, so for you to easily recall that if it is negative sign, it is about gaining or adding electrons, you have to recall the charge of this particle. What is again the charge of electron? Is it a positive or a negative particle of atom? Electron, electron. Yes, electron are the positive or negative particles of atom. Yes.
Negative.
Electrons, okay, they carry negative signs. Okay, so for you to not confuse it with having a negative sign as subtracting or a minus na sign, recall the charge of electrons. It's negative charge. So when we say an atom gains electron, it is more on adding negativity because it gains electron and electrons carries negative charge. So if that atom gains more and more electron is negative. Therefore, what happens to that atom? It will also carry negative charge. Tama? That's correct, right? So you simply recall for the sign, the charge of the electron. Okay, so what we are talking about is electron, the losing and the gaining of electron. So if that atom then loses electron, what happens to the electron? Being removed. It is being reduced from the atom. So what happens now to that atom? If you reduce the negativity, you reduce the negative charges, it will now carry positive charge. Okay, so you just go back to the charge of the electron. Do not confuse the signs with what you know about operations. Kasi I know some of you might be confused na kapag positive charge is adding, negative charge is subtracting. So do not confuse that with mathematical operations. Okay? Sige. So if sodium ion carries a positive charge, then it loses or gains electron. Lose or gain? Yes? So this time it
Lose.
okay, so it loses electron. So it loses electron, particularly one electron, because it has no value, no numerical value. So imaginary one. So it loses particularly one electron. Therefore, if you are asked for the number of electrons for the ion form of sodium, how many do you think would be the total number of electrons for the ion sodium? It's not anymore 11. Total of what's your answer?
10.
Okay, 10. Very good. So total of 10 electrons. So that's how you identify the number of electrons if it's already charged. It will vary if the given atom is already charged. Okay, let's have another example. Let's say yung previous atom I have provided, chlorine. So this time, I will give the ion form of chlorine. So it's the chloride ion, that's the ion form of chlorine. And if you will be asked for the total number of electrons here, and since it carries a negative charge, meaning to say it gains, right? It gains one electron. So you tell me what's the total number of electrons here for chloride?
18.
Okay, total of 18 electrons. So that's it. Okay, last example. Aluminum. If you try to refer to your notes about list of ions, aluminum has ion form aluminum 3 plus. That's the ion form of aluminum. And therefore, it carries a positive charge, so it loses 3 electrons during chemical reaction. Okay, so total number of electrons here would become, by the way, aluminum, its atomic number in your periodic table, I think that's 13. Okay, 13. Okay, so this will be your reference. So how many would be the total number of electrons this time? Mm-hmm. It loses 3 electrons, so total of, okay, so same with sodium. So 10 electrons. Okay, so for the proton number as is, kasi what's the atomic number, atomic number, that's equivalent to the proton. proton number won't change. Okay, it won't change. It's equivalent to the atomic number. So proton number here is 11, proton number here 17. Mm, for aluminum, it's 13. Okay, so that's it. That's how you determine the number of electrons if charged atom. And then for neutral again, neutral atom, proton is just equivalent to the number of electron. Okay, now let us proceed to our next topic. Let's talk about quantum number. But before I introduce it, four set of quantum numbers, let's have first this slide. Please take note that when in chemistry, what is being studied or what concept that is being studied in chemistry, if you talk about arrangement of electrons in an atom, the concept that will be studied would be quantum numbers. Okay, so we'll talk about electron distribution, how electrons are being arranged uh, in an atom, what are the locations of electrons in an atom, or what's the energy level of electrons being distributed in an atom. Okay, please take note, class, that the electrons, as you all know, they surrounds the nucleus of an atom. They are placed farther away from the nucleus of the atom. So they are the ones found outside, surrounding the nucleus. And particularly the electrons surrounding that nucleus, they occupy a particular shells. Okay, they occupy what we call subshells, or known also as atomic orbitals. So let me write it first, the definition. Uh, Atomic orbitals, that's the region in space around the nucleus where there is a highest probability of finding an electron. Probability of finding an electron. So you can copy again. Let me read. Atomic orbital, or the subshells that I am referring to, where electrons tend to occupy, these are the regions in space around the nucleus where there is a highest probability of finding electron. And these are the atomic orbitals available. So we have the S subshell, the P subshell, the D or sublevel, the D subshell, and then the F subshell. So we have the SPDF, and as you all can observe, they have different shapes, particularly for the S subshell, it has spherical shape. The P subshell, it looks like a dumbbell shape. For D subshell, it looks like a clover leaf, no, clover leaf-like shape. For the F subshell, perpendicular to each other, perpendicular to each other, meaning whatever the shape uh, on top, the same parallel to the bottom part, perpendicular to each other. Okay, what else? Please take note also for now, although we will have a thorough discussion later on, take note for now that for S subshell, it contains only one orbital. Any S subshell that you will encounter later on upon writing electronic configuration of an atom, they contain only one orbital. For P subshell, three orbitals. Let's say, for example, hypothetical, yung illustration, the boxes that I am drawing, this represents orbitals. Okay. And then for D subshells, it consists five orbitals. And then for F subshell, total of seven. One, two, five, then six, seven. So seven orbitals for F subshell. Five orbitals for D, three for P subshell, and then one only for S subshell. All right. Another thing you have to take note, each orbital that I represent in a form of boxes, they can hold up to two electrons only. They can hold up to a maximum of two electrons only. Okay, so meaning per boxes, so per orbital, they can hold up to two electrons. So let's say I will uh, occupy maximum of two electrons for each boxes. So for S sub level, we could tell that maximum of two electrons it can hold for an S sub level kasi it only contains one orbital. What about for P subshell? 1, 2, 3, 4, 5, 6. So total of 6 electrons that it can hold for any P subshell. It can hold up until 6 electrons. You tell me for D subshell, total of how many? Okay, total of 10. Okay, total of 10 electrons. And lastly, for F subshell, total of 14. Okay, so 14 electrons. All right. So we'll have a thorough discussion later on as I present the different set of quantum numbers for you to better understand why, for instance, an S sublevel has only one orbital, why a P sublevel only has three orbitals, so on and so forth. Okay, so we actually have four sets of quantum numbers that describes atomic orbital. Particularly, it's the first three. The first three quantum numbers describe the atomic orbital. Atomic orbital. They describe particularly the shape, the uh, the orientation of the atomic orbital, okay, and even the size, of the atom itself. So the first three that I will introduce later on, they focuses more on the atomic orbital. Whereas the fourth quantum number, it specifically describes the electron spin, the behavior, okay, the behavior of the electron. All right. So again, the first three, they describe the arrangement of the electron or the atomic orbital. Fourth quantum number, it's about the electron spin. Okay, so let's begin with the first quantum number. The first quantum number is known as principal quantum number, and it is designated with small letter n, or it's the symbol of principal quantum number. And a it could have any positive integer value, and that would be 1, 2, 3, so on and so forth. When you say positive integer value, not included, zero is not included. Okay, and it should not be in a fraction form, not fraction, not in decimal point, and again I repeat, zero is not included. Okay, so those are the possible values of the first quantum number, the principal quantum number. So what's the importance of principal quantum number? It describes the main energy level, or the highest energy level of an atom. Or when you say highest energy level, it describes the last shell, okay, the last shell surrounding the nucleus of an atom. And that is where we could find the valence electron. That is where valence electron, or also known as the outermost electron, occupies. Outermost electron occupies. Okay, so later, when we learn about electronic configuration, you'll be able to encounter again this term, valence electron. So for now, just know that these are the set of electrons found in the outermost part of the atom, found in the highest energy level, the last shell, okay, surrounding the atom. Okay. Now, in the periodic table, let me show you a periodic table. Excuse me. For a while. Okay. Periodic table. It's here. And then, okay. So, ayan. Now, in the periodic table class, for you to determine the n value of an atom, meaning the highest energy level of a particular atom, you just refer to the period number. Remember that the atoms of the element, aside from grouping them vertically, we also have another way to group the atoms horizontally. So, yung horizontal row, ito yung pa horizontal way of grouping, that's the period, the period number of the atom. So which period that atom resides, that's the n value or the principal quantum number. Okay, sige nga, let me ask you, what's the n value of hydrogen? If you will be asked, what's the n value of hydrogen? So you refer to the period. Yes? Period. What period? Is it 1, 2, 3, 4? So on and so forth. 1. Okay, it is found in period 1. Okay, what about aluminum? Aluminum, if you will be asked, what's the N value of the atom aluminum? Then look for aluminum, what period it resides. Okay, it resides at period 3. So the horizontal one, no, the horizontal row. That's it. Do not worry during examination. You will be provided, maybe at the last page of the questionnaire during examination, a periodic table. So you don't have to memorize, no, which period that atom resides in the periodic table, just to identify the n value. No, you will be provided with a periodic table, but not a periodic table with complete details. Okay. Uh, just a periodic table that is intended for examination. Okay, intended for examination. Sige. So again, that's how you identify the n value, the horizontal row. Next, another importance of the n value of the atom is that it indicates the size and then the distance, the size of the atom and then the distance of the electron from its nucleus. Okay, so we could tell that the greater the n value of that atom, it would have greater energy level or higher energy level. And what happens to the size of the atom? It will have greater, larger size, and the location of the valence electron would be farther from its nucleus. So let me illustrate it for you to better understand the relationship, its relationship to the size and then the distance of the electron. Okay, let's say this atom represents hydrogen. So example, that's the nucleus of the atom hydrogen. Diba the nucleus is the center part of the atom. And then it says here that it has an n value of 1, meaning to say that's the energy level. The energy level meaning the shell, the number of shell for that atom. So it only has one shell surrounding its nucleus. And that is where you can find the valence electron of that hydrogen. Okay, kasi it only contains one n value. Okay, what about for aluminum? Okay, if this is aluminum, the nucleus of aluminum, from its nucleus, it contains three shells. Okay, so 1, 2, and 3. So its highest energy level would be 3 because that is where we could find the valence electron. Okay, again, I told you earlier, the last shell, the highest energy level, that is where we could find the valence electron, the outermost electron of that particular atom. Okay, Now try to observe this time the size of the two atoms that I illustrated, hydrogen versus aluminum. Obviously, the one that has larger size is aluminum. Okay? And it makes sense because based on this statement, the greater the n value, what happens to the size of the atom, the larger would be the size of the atom. That's why when I illustrate it, it's evident that aluminum would have larger size than hydrogen because aluminum has higher n value, greater n value. So the one with the larger size. And what would happen to the distance of the electrons from its nucleus? It would be farther kasi the larger the size of that atom, then we could tell the distance, the location of the electrons would be farther from the nucleus. Okay, so that's the relationship between the n value towards energy level, size, and location of the electrons. Okay, so that's the first principle, the first quantum number, the principal quantum number. Okay, next, let's proceed to so this is just an example. The second quantum number, also known as angular momentum quantum number or the azimuthal quantum number. Now this one, it is designated with italic L. Okay, so parang ganito. Okay, italic L. Small letter L in italic, written in italic. Okay, so the values for angular momentum quantum number, it could be any integer value from 0 up to n minus 1. So your reference point or the one or the value that dictates or limits L would be the n value. Okay, so take note, it's the n that limits or dictates the L value. Okay, and please take note that each L value that will result to, it is designated with a letter. It is designated with a letter. So please take note, uh, the L values, it has letter designation. So letter used. So for example, if L is 0, the letter designated to that value is S. If L is 1, P, 2 is D, and finally 3, F. Okay, so I have introduced this earlier, these letters, SPDF. Remember, they have different shapes. Okay, that is why for angular momentum, its importance is it determines the shape of the atomic orbital. Because remember each atomic orbital, they have different shapes. So for S, let's recall, it has spherical shape, and then for P, it has dumbbell shape, and then for D, clover leaf-like shape. It looks like a clover leaf. And then the F subshell, it has perpendicular shape. Okay. Oops. All right. So please take note of this, that each L value, it has a designated letter. Okay. Now, just a very short historical background where these letters originated from. Uh, these letters as PDF, they came from the words sharp, uh, P, it's principal, yeah, it's principal, and then D, diffuse, F, fundamental. So I repeat, these these are the words. These were the words where these letters came from: sharp, principal, diffuse, and fundamental. Now, before the quantum mechanical model was proposed by Erwin Schrödinger, he was the one, but he was the one who proposed that model. That's why we have this set of quantum numbers. Right before the quantum mechanics were developed, these words were already used. Okay, particularly they describe spectra. Okay, or what we call spectra lines, or features of spectra if a particular sample or a particular particle is being subject to qualitative analysis. So these were the words used to describe those spectra that resulted from the qualitative analysis of certain particles or certain samples. Now, right after quantum mechanics was developed, what happens is the first letter of each word were just adopted. So they were just adopted by the time the quantum mechanics was developed, and this time this letter would intend to describe a shape. Okay, so again, this time, uh, the first letters, or these letters, they describe a particular shape, a shape of the atomic orbital. Okay, so that's the history why we use these letters. They were just adopted, okay, from these words: sharp, principal, diffuse, and fundamental. All right, so let's try to determine, no, how to identify values of angular momentum quantum number. Okay, let's extract the given example I provided earlier, aluminum. Diba? Let's recall, aluminum has n value of 3. Now let's identify the L value. Okay, going back to this part, the L value is from 0 up to n minus 1. So you have 0 up to n minus 1. So we need the n value to identify the complete values for L. Okay, so the given n value for aluminum is 3. So you substitute there 3 minus 1. So that means from 0 up to 2, right? Okay, 3 minus 1, 2. So you complete the numbers. What are the numbers from 0 up to 2? So that would be 0, 1, and 2. So you have to provide the complete numbers, or values: 0, 1, and 2. So these are the L values: 0, 1, 2. Okay? And again, what's the importance of these values? This quantum number, they describe shape, meaning for each value of L, there is a designated letter, and each letter describes a particular shape, a shape of the atomic orbital. Sige, you tell me, if L is 2, what's the letter designation if L is 2? I'll try to assess if you follow the discussion. Yes. If L is 2, the letter designation is okay. I sorry. Okay, that's sorry. Ayan. It's D. Okay, correct. And then if it is 1, let me place it in a parenthesis. So D. If it's 1, that would be P. If it's 0, that is S. Okay, so that's the importance of L value. Okay, so going back, if the N value, it represents the energy level, the main energy level, the size, and then the distance of the electron from the nucleus, the L value would describe the shape. Okay, kindly highlight this in your notes, the shape of the atomic orbital. If it is S, spherical. It's P, dumbbell shape, so on and so forth. Okay, you will also be asked, no? There are questions you will be asked for the sub-level designation or the sublevel name given only the N and the L value. So how will you write the sublevel name? The sublevel name will only consist of, let me erase this part. Okay. Ayan. Now, regarding the sublevel name, that consists only of the N value. Listen, the N value, meaning the number, okay, the value that represents the N. And then followed by the letter that designates L value. The letter that designates the L value. That's what you need to identify the sublevel name, given only the N and the L. Therefore, for this N and L value, we could tell that its sublevel name would be 3S. Sorry. Okay. Again, for the sublevel name, for the first set, if N is 3, L is 0, it's 3S. So again, you just need the value of the N and then the letter that designates the L value. If L is 0, diba, it's S. Okay, next. For this given N and L, that would be 3P. And then last, this would be 3D. Okay, again, this 3 represents the N, and then these letters followed by the N value are the letters that designates each L value. All right, so that's it. What else? In the periodic table, let me show it again. Here. Okay. You can also identify, no, based on the arrangement of the atoms in the periodic table, which of which atoms uh, ends with an S orbital, P orbital, D orbital, or an F orbital. So they actually have a blocking arrangement in the periodic table. So please take note, this first two columns, they fall under S block. So later on, when we write, or in your laboratory, maybe you had your laboratory activity already about electronic configuration. Upon writing the electronic configuration of the atoms, you'll find out that the last uh, outermost shell of these atom that falls under this block, they end with S orbital. Okay, and then for this portion, these are the P block, and then D block, the middle portion, and then this part, F block. Okay, so we'll have a separate segment discussion about electronic configuration. So we can recall this blocking. So just take note of the blocking: the S block, the P block, D block, and F block. Okay, so that's it for the second quantum number. Let's proceed with the third one. So these are just example, okay, which I provided earlier. If L is 0S, if L is 1P, 2D, and F, L is 3. Okay. Okay, let's have the third quantum number, the magnetic quantum number, or this is designated with M sub L. Okay. Now, please take note that this quantum number, the one that dictates its value is the L. Okay, so the L value dictates or limits the M sub L. Okay, so you need the value of L. That's why, diba, you have to determine first from the very beginning the N value to get the L. And then you need the L value to determine the M sub L value. So that's the order of quantum number. Okay, it should be in chronological order. Principal first, then azimuthal, followed by magnetic quantum number. Okay, so what's the importance of this magnetic quantum number? It describes the orientation. Okay, the orientation of the orbitals in space around the nucleus. Okay, example. Okay, let's go back to aluminum. We'll just continue the example that we have provided earlier. Again, it has an n value of n value of 3, and then the L values are 0, 1, and 2. When we write its sub-level name, that is 3s, 3p, 3d. Now, let's proceed to the m sub L value, focusing on the third quantum number. To get that, it should have values from negative L, 0, and positive L. Okay, so you need this as your reference point to identify m sub L's, okay, or m sub L values. So if L is 0, take note, if L is 0, of course, it don't, a 0, a value 0 don't have a negative and a positive charge, so only 0. Okay, so you simply write here, its m sub L would be 0. Okay, given the L, which is 0. Okay, proceed to L is 1. If L is 1, of course, the value 1 has a negative and a positive. Okay, so it should be from negative 1 followed by 0 to positive 1. Okay, so that's how you write the m sub L values. From negative L to 0 to positive L. Okay, next. If L is 2, okay, if L is 2, so from negative 2, followed by, what's next to negative 2? Diba? Negative 1. Followed by 0, then go on with the positive 1, and positive 2. Alright, so that's how you write the m sub L values. Okay. Another importance of m sub L values is the total number, that total number of m sub L values that resulted, that is also equivalent to the total number of orbitals in subshells. Okay, let's go back to what I have introduced earlier when I showed when I show you the different shapes of the atomic orbital. Diba? I told you that the S sub-level, it only contains one orbital, right? The P sub-level, three orbitals. Okay, so on and so forth. Now, the reason why the S sub-level has only one orbital, it is because only one sub-L value we got, okay, for an S. Try to check. You simply count. There's only one value, one M sub-L value under S, okay, under S sub-level. It's only one value, which is 0. So you write it, number of orbitals, 1. Okay? Again, the number of M sub L values that it resulted, it's also equivalent to the number of orbitals in that subshell. The subshells we are referring to are S, P, D, F. Okay? Next, for a P subshell, try to look at the number of M sub L values that you got. You have 1, you count it, 2, and then 3. So 3 values, 3 M sub L values. So total of 3. That is why I told you for a P sub-level, there are 3 orbitals for P sub-level. Kasi based on this presented data, diba, we got how many values? We got 3 M sub L values, 3 M sub L values for P, okay, for P sub-level. And that's equivalent to the number of orbitals in the P subshell. Okay, next. for D. For D sublevel, as you can observe, the number of M sub L values that we got, 1, 2, 3, 4, and 5. There are a total of 5 M sub L values. So that total number of M sub L values that you got, that's also the total number of orbitals in the D subshell. So that's why when I introduced earlier, 'di ba, sa patong the first slide that I have shown you, the D sublevel has five orbitals. All right. Next, recall also. Try to recall per orbital. Per orbital, how many maximum of electrons again could occupy? How many maximum of electrons could occupy for each orbital? Let's say this box represent an orbital. Yes, only two. Only two electrons can occupy per orbital. Now, if we add column here for the maximum number of electrons that could be occupied for each sublevels, if you will be asked for S, this one for S, total of 2. You continue. Kapag P, there are 3 orbitals for P. So how many? Maximum number of electrons. Total of, okay, 6. All right. And then lastly, for D subshell, there are a total of 5 orbitals. So the maximum number of electrons it can hold up to 10. Okay. Very good. So that's the importance of magnetic quantum number or the M sub L. Okay, so overall, those are the quantum numbers that describes the distribution of the electron or the atomic orbital. Okay, again, the magnetic quantum number, this describes the orientation. The azimuthal or angular momentum quantum number, it's described the shape. And the principal quantum number, it describes the highest energy level. It is also relative to the size of the atom and then the distance of the electron around the nucleus. And then let's proceed to the fourth quantum number. Again, this quantum number, it has nothing to do with the atomic orbital. So later on, if you will be asked during examination, which of the following quantum number do not describe at all, do not describe atomic orbital at all. So that would be electron spin or the M sub S. Okay, so that's the designation or the symbol for electron spin quantum number, M sub S. So it describes specifically the behavior of the electron, okay, or the magnetic spin of the electron, which could have the following values: positive half or negative 1/2. Okay, now why does it have this values 1/2? Okay, in basic chemistry references, electrons can be classified as fermion. When you describe a fermion, it's a particle whose spin number is an odd multiple of 1/2. Okay, that is why it has this value, 1/2. Okay, so that's the reason it is classified as fermion. And apart from that, electrons is also considered a vector. Diba? In physics, how do you describe a vector? It has a magnitude, it has a value, and it has a direction. A direction here would be this signs positive and the negative signs. That represents or indicates direction. Let's say, for example, if it is a positive sign, it tells us an upward direction. And then if it is negative sign, it tells us a downward direction. Okay. Take note also that because of electron spin, whenever the electrons occupy a particular orbital, they should have opposite spins. Okay. So it follows under the rule Pauli's exclusion principle. This one, Pauli's exclusion principle. Okay, it states that there, let me write it. Principle. Okay, it states that no two electrons can have the same set of quantum numbers. At least they differ with their spin. So let me write it. No two electrons can have same set of quantum numbers. At least they differ on spin. Okay, so they may have the same uh, principal, azimuthal, or magnetic quantum number, but when it comes to electron spin, no two electrons can have same set of spin. Okay, they should have different orientation of spin when they occupy a particular orbital. That is why by practice, when I illustrate electrons occupying a particular orbital, this is how I write it. Only half arrow-headed, okay, or half-headed nga arrow. Half-headed arrow. Okay, that is to for me to recall that the value of the electron spin is one half. That's why I only write it this way. Okay, an arrow that is half-headed. So upward orientation, that's positive one half, then downward orientation, that would be negative one half. All right. So that's all for the quantum numbers. Again, recalling all of them, we have the principal, the azimuthal, and or the angular, and then the magnetic quantum number. This three describes atomic orbital, and then last one would be electron spin. Okay. Uh, I was able to discuss this already. Okay, let's review. Okay, an example of an atom with this n value would be carbon. You can check in your periodic table, no? Any atom that falls under period 2. So example, carbon. Carbon falls under period 2, so it would carry the n value of 2. And what would be the L values? How do you get L value again? Let's recall from 0 to n minus 1. So you simply substitute here 2 minus 1. So from 0 to 1. Because 2 minus 1 is 1. So 0 to 1. So you have 0 and 1. Sublevel name, you need the n value and the letter designating that L value. Recall that if L is 0, that is S. If L is 1, that is P. Okay, that's why you have this sub-level name, 2S and 2P. The M sub L values, recalling uh, the way how to determine the values of M sub L, negative L, 0 to positive L. So this will be your reference point. Look for the L value. If L is 0, then you just write 0. There's no such thing as negative 0 or positive 0, right? So write only 0. If L is 1, and that's the time you have negative 1, then followed by 0 and 1. Okay? And the importance of these M sub L values. Whatever the number of M sub L values that you got, that is the total number of orbitals per sublevel. You simply count. You have 1 value. So you write 1. You have 1, 2, 3. So 3 M sub L values. That's the total number of orbitals for that sublevel. The number of electrons per sublevel. How do you get this? Recall that per orbital, 2 electrons can occupy. Okay? So for the S sublevel, since it contains 1 orbital only, so times 2, kasi 2 electrons can occupy 2 electrons can occupy in that orbital. So total of 2. And then for p sublevel, there are 3 orbitals in that sublevel. So times 2, total of 6. All right. And then next, okay, let's try to identify. For each quantum number, you just have to state which part is invalid and why. Actually, the answers are reflected already in your PDF handout. So let's try to answer. If n is 1, just answer ha if is it correct. If n is 1, is it correct that the L value, uh, one L value that you can get is 1? Yes or no? Is this correct? If the given is 1 for the n value, okay, do you get also the L value of 1? Okay, okay, this is false, no? This is invalid. This is wrong kasi, remember, if n is 1, to get the L value, it should be from 0. 0 to n minus 1. So 0 to n minus 1. So you substitute here 1. 1 minus 1 is 0. So only 0. The L value should only be 0. So this is invalidated. So the rest are correct. Okay. And then the following, you can just assess this during your independent study. All right. Do you